It is a pleasure to get to present some recent work on recovering the position and width of the covert attentional window. It has long been known that focal spatial attention can enhance behavioral responses. We have a general intuition that we can spread this so-called spotlight of attention over regions of space of varying sizes. Spreading the attentional spotlight would predict results like those shown here, wherein behavioral enhancement decreases with attention field size. These behavioral changes may be due to increases in the gain of visual responses in early visual cortex. There is some neuroimaging evidence suggesting that wider attentional windows broaden the extent of neural activation, as shown here. However, recent EEG work has shown that wider attentional windows result in a decreased amplitude of the attentional enhancement rather than broader activation. Therefore, we sought to investigate whether the breadth of the attentional enhancement really does increase with larger attentional fields. So for today's talk, I'm going to first tell you about the novel task we developed that manipulates the position and width of the attentional field. I'll then discuss a model we developed to recover both the position and the width of the attentional window from bold data. And finally, I will show you how the model performs at progressively smaller temporal windows. So to start, we developed a spatial integration task in which participants fixated at the center of the screen and were asked to determine whether there were more digits or letters in a cued region of the circle. The cue was always valid, and there was a 50-50 chance of more digits or letters on each trial. Throughout the task, there was a ring of visual white noise present on the screen as well. For each trial, the participant would see the cue for 1.35 seconds before the letters and digits appeared for half a second. This was followed by a response window in which participants indicated via button press whether there were more digits or letters. There were always 20 digits and letters equally spaced in the display, and the cue could be centered on any of the locations. The cue could also have one of four widths spanning 1, 3, 5, or 9 locations. Participants experienced blocks of 5 trials with a stable cue position and width, lasting 15.5 seconds, before moving directly onto the next block with a different attentional cue. All participants completed a minimum of 8 runs of the task, equivalent to 800 trials, while in an MRI scanner. Though this illustration is not to scale, you can see an approximation of the 4 cue widths. In this example, they are all centered on the same location, but their width varies. So to give you a better feel for the task, this is an example of what the participants experienced. It starts with a cue spanning 5 locations, centered on 90 degrees. After one block of 5 trials, the cue switches to a new location and becomes narrow, spanning only 1 location. You'll likely notice that the smaller the cue, the easier the task is. And this was borne out behaviorally. Participants were most accurate for the narrowest cues, though they were above chance for all widths. For our analysis, we relied on population receptive field, or PRF, data collected for each participant independently. We selected voxels in areas V1 through V3 for which the receptive fields overlapped the white noise ring. In addition, we also selected the top 10% of voxels based on their significance from an independent localizer task. That procedure left us with a set of voxels spanning the white noise ring, as displayed here for one example participant's area V3. We began by first determining whether there were width or amplitude differences in our bold signals based on the width of the attentional cue. Here, we're showing average bold response as a function of polar angle. We averaged our data separated by cue width, recentered based on the position of the attentional cue. As the cue gets wider, we see both a broadening of the attentional modulation of visual activity, as well as a drop in amplitude, despite the fact that visual stimuli were presented across the whole range in all conditions. These results were obtained by averaging across the whole session, which included a minimum of 800 trials per participant. This confirms that attentional enhancement does become broader and decrease in amplitude for larger attentional fields. Area V3 showed the strongest effects, but we saw similar results in V2 and weaker effects in V1. Therefore, for the remainder of the talk, I'll focus on results from V3, though we performed the analyses for all 3 regions. So for all of these analyses, as well as the prior results we've highlighted, we've relied on averaging over many trials or long periods of time. However, it is unlikely that participants' attentional windows were deployed in exactly the same manner on every trial. Therefore, we next sought to investigate the attentional window at different timescales. So in thinking about this question, it is obvious that with less data, the size and shape of the attentional window will be harder to detect. But more substantively, temporal limits could also emerge from a consistent narrow window of attention sampling broader regions of space. So if you imagine that you're cued to attend to this gray region of space, You could use a small attentional spotlight and sample the region over time, such that averaging would show a broad attentional enhancement. Alternatively, the spotlight itself could be broader, meaning that even at short timescales, the attentional enhancement would be spread over a larger region. So to address this question, we arranged our selected voxels based on their PRF polar angle, and then fit a von Mises or circular Gaussian distribution to the data. The von Mises distribution can be characterized by 4 parameters: mu, which indicates the center of the distribution, sigma, which indicates its standard deviation, as well as amplitude and baseline parameters. To illustrate this, we're showing an example bold response to a stable attentional cue averaged over one block lasting 15.5 seconds. Each black point represents the average bold response for one voxel. The shaded region shows the cued region of the display. There is a clear peak in the response around the cued region, and this is borne out by our model shown in red. For each model fit, mu can serve as an indicator of the position of the attentional window, and sigma can indicate the width. We performed this model fitting procedure on blocks of 10 TRs independently. So to quantify the performance of the model, we first looked at the error between our model estimated position of the attentional window and the actual cued position. Here, we're showing a histogram of the position error for the widest condition spanning 9 locations. This is averaged over 3 participants. There is a clear peak at 0, though there are also large tails. We've next overlaid the error distribution for the width condition of 5. This has an even taller and narrower peak at 0. For the width condition of 3, the peak is again narrower and taller. And finally, our narrowest cue shows the narrowest error distribution. Overall, this indicates that our model does an excellent job of recovering the position of the attentional window across all cue widths. Importantly, though we see differences between the width conditions, this does not itself indicate a broadening of the attentional window. It instead illustrates that the model estimated position deviated more from the center for the wider attentional cues. So next, to assess the width directly, we turn to our model estimated width of the attentional window. The distribution of sigma for the widest attentional cue is shown here, averaged over 3 participants. There is a broad peak toward the narrow end of the distribution, and then a large peak at the maximum width, which is essentially equivalent to attending to the whole ring. The median is shown in a dashed vertical line over the top. So as before, we've overlaid the distribution for the width condition of 5. The median is notably smaller. The width condition of 3 has a very similar median, while the narrowest width condition shows a markedly smaller median, as we see in the overall shift of this distribution toward narrower widths. Overall, these width estimates are highly variable within all conditions, though there are differences between them. We can also visualize these medians per participant, shown in the warm colors, as well as the group mean, shown in black. We can compare them to the actual width of the cue, indicated by the dashed gray line. Though the width estimates increase with cue width, they do not mimic the actual width of the cue. So given that the model recovered our parameters of interest well when averaging over blocks of 10 TRs, we next wanted to determine whether it would continue to do so at even shorter timescales. So we followed the same procedure, but fit the model to the smallest possible time unit, which is a single TR lasting 1.55 seconds. Here, we're showing the same sort of error distribution as before. For the widest condition, though there is still a peak at 0, there are larger tails that more gradually decline. For the width condition of 5, the peak is again narrower and taller, even more so for the width of 3, and more so for the narrowest width. These clear peaks show that even at the single TR level, the model can robustly recover the position of the attentional window. If we compare these error distributions to the one from the block averages, the model still does a remarkably good job at estimating the position of the attentional window. But how does the model fare when it comes to width at these shortest timescales? When we look at the median width estimates separated by width condition, we see much smaller differences. The comparison to our 10 TR average data drives this home even more. Whereas the 10 TR average shows a clear increase in width estimates as the attentional cue widens, individual TR estimates do not show this pattern. So to explore the temporal limits further, we parametrically varied the number of TRs included in the average. We can plot the group average over here on the left as we step through increasing temporal windows. So for 2 TRs, or 3.1 seconds, we see a slightly greater increase in width estimates as the cue broadens. 3 TRs, or 4.65 seconds, shows a more notable increase, especially over the narrower 3 cues. The widest cue seems a bit more variable across participants. This is increasingly true for 5 TRs, or 7.75 seconds. And at a full block of 10 TRs, or 15.5 seconds, as shown before, we see the largest differences in the model-derived width estimates between the conditions. We also see the greatest variability between participants for the widest cue. So to quantify these differences another way, we fit a line to this data and plotted the slope as shown here. As the timescale increases and more TRs are included in the average, the slope of the fit line increases and width estimates become more distinguishable. Though there is clearly substantial intersubject variability, this is largely driven by the widest Q and our small n, and it is generally clear that more temporal averaging allows us to see greater differences in the width of the attentional window. So overall, averaging over the whole session, we observed both a broadening of the attentional enhancement and a decrease in amplitude with wider attentional cues. Our dynamic spotlight model robustly recovered the position of the attentional window, even at our shortest timescale of 1.55 seconds. We also found that width differences can be reliably recovered, but only at longer timescales. There are a couple of reasons why this could be true. First, noise could be corrupting our ability to recover the width. Based on simulations we performed, if attentional gain decreases with broader attentional windows, noise would be especially problematic in recovering accurate width estimates. It would therefore make sense that our model performance improves with averaging, as this decreases the influence of noise. Alternatively, participants could instead employ a consistent narrow window of attention that they use to sample the space. If this were the case, then we could expect to see consistent narrow width estimates at our shortest timescale, and a broadening due to averaging as our timescale increases. Identifying to what extent these explanations factor into our results is a top priority for our future work. So in closing, I'd like to thank my collaborators, Ilona Bloom, Sam Ling, and Joe McGuire for their invaluable contributions to this project. I'd also like to acknowledge our funding sources and thank you very much for your attention.